Electrical transformers are a major part of our life, from how we get electricity to our homes to how we convert mains AC to specific voltages for our appliances and our personal devices. So, what is a transformer? Well, it's a passive component. It transfers electrical energy from one circuit to another. They're usually step up, step down, or isolation, moving AC current to different voltages. The varying current of AC causes magnetic flux, which induces EMF or electromotive force from one coil to another, although the coils themselves aren't physically connected. This has to do with Faraday's law of induction, which states that a changing magnetic force can induce electric current in a circuit. Electromagnetic induction was independently discovered by both Faraday in 1831 and Henry in 1832. Early induction coils determined the ratio between windings in a main coil and a secondary coil, which caused a larger induction in the secondary coil. Early induction coils used direct current since AC wasn't available into the 1870s. You had to use an interrupter for DC to interrupt and to constantly change current. DC on a transformer without an interrupter can cause a lot of problems. You've got overheating, excess voltage, etc., because it's not alternating. When alternating current became a thing, it removed the need for the interrupter, as alternating current simply did this naturally. Now, let's use the example of a power grid in North America. You've got power being generated at anywhere from 13.8 kilovolts to 25 kilovolts at 60 hertz. It steps it up to 115, all the way as high as 765 kilovolts, and this is for to allow it for a long distance transmission. It arrives at a local substation or local transmission substation where it's stepped down from say 345 kilovolts to 138 kilovolts. When it goes to the distribution substation, it's further stepped down, going from like 138 to say 13.2. And then utility transformers, they can be poles or pads. You live in the suburbs or anyone where you see a telephone pole and you see those little pill capsule looking containers, that's what I'm talking about. They may take something from as high as 14.4 kilovolts to as low as 17.2 kilovolts and steps it down further to 120 volts and 240 volts, respectively. And that goes into individual homes. 120 volts that can be used for lighting, computers, modern TVs, smaller appliances, some refrigerators, freezers. And then 240 volts is electric dryers, ovens, water heaters, electric pumps, heat pumps, EV chargers. And then you can take that further with a phone charger that has an internal transformer switch mode power supply, steps that 120 down to 5 to 20 volts DC, also converting it to DC, I should add. And then a laptop charger might do the same and bring it down to 19 or 20 volts DC. A microwave oven, on the other hand, actually has to step it up to 2 to 4,000 volts AC to generate the microwaves. Now, what are some of the types of transformers out there? Well, there's core types. They have two coils with windings of wires around them. This is kind of the default type, um, and it's generally made for high voltages. You've got shell type, where the core actually surrounds the windings. That offers a lot better protection, mechanical strength, a much more compact design. You can have two windings, which is typical design, or you can have something like an auto transformer that has a single winding around both coils. You can in terms of cooling solutions, you can do like dry or air cooling, but you must also do oil immersed. Um, you have isolation transformers. That's for isolating circuits from one another, improves safety, reduces noise, etc. Impedance matching ones that just matches impedance between circuits. You'll see that a lot for audio systems. Um, Pulse transformers, those transfer pulse with minimal distortion. You'll see those in electronics, digital circuits. You've even got variable transistors, Varax, and that allows for adjustment of output voltage. You'll see that used in labs testing equipment. We've also got transformers either that are one phase or even three phase. And we'll be talking about one phase and three phase in a future video. Now, in terms of coils and windings, the simplest thing, take a single magnetic core, usually made of iron, and you have two sets of windings on either side, primary and secondary. You've got primary coil windings or NP turns. You got secondary coil windings or NS turns. But with an auto transformer, you just use one set of windings where the inputs and outputs are simply applied to different sections of the windings depending on what desired ratio you want, instead of there being two windings. The core is often iron, and the winding coils are usually copper or aluminum. Here's the general formulas for the volt ampere ratings. There's a different one for three phase, which again, and we'll get into in a future video. All right, we're here on every circuit. I've got two set up, but let's just look at the one on the left. It's just a 1-for-1 winding to keep it simple. We've got 60 hertz, 120 volts on the left side. We've got uh, both taps on the right, individual paths, both 1000 ohm resistor and then ground. Let's take a look. The blue is the original signal, and then the other two colors are at split. You'll notice 240 because it's going 120 positive, 120 negative at 60 hertz, and then these are split between the two halves here, about 120 volts, 120 volts here, and they're completely out of phase with each other, 180 degrees. This is important. While one's pushing, the other's pulling. One line's positive, the other's negative. Okay. All right. So let's now look at. Just turn those off for the moment. We'll look at a center tapped. Same idea, but we have a tap in the middle as well. So you've got three. So, and then one's at the two extremes. All right. Pretty simple. Same idea as we have over on the left. And then in the middle, we have nothing. So positive, zero, negative. All right. Let's cut this half off. Actually, before I do that, you know what? Let's move this up to, I don't know, 10 or 100. Let's see where that goes. So we're actually seeing something now instead of just 100. All right. So we're seeing pretty even split now between the middle and the bottom. And then the rest is on the top. Well, let's move that even further. At that point, it's not really mattering. We're still getting basically the same numbers. All right, let's cut off one and see what where we're going to see the difference. Now, it's still going to this tap, so cutting it off isn't going to make much of a difference. But we still got the basic idea. The numbers actually haven't changed. All right, let's make some adjustments to the winding to see what we can get. Now, in this case, I mean, it's all the same. I mean, it's just splitting it. So I don't know. Let's change it to, let's say 19. What happens when we get that? Let's get rid of all that. All right, that's changing the range to 6.3, whatever. I don't know, 19.5. How's that going to change? That's primary terms. And it is a ratio. You want to reduce it, maybe? Goes the other direction. S- 10 to 1. So let's move it back to 1. 1 to 1. Change the other one to 19. Oh, no, that's going to step up. Okay. But yeah, anyways, yeah, we could step it up quite a bit, actually. 15, maybe. Okay, that makes it up to 8 volts. 16, 20. To 25. Okay, maybe 23, 24. Okay, about as close as I'm going to get to about 5 volts here. So yeah, we've done a step down. It's still AC though, so that'll be a subject of another video, converting AC to DC. Now keep in mind this is a really simplified model. All right, let's look at Falstad and transformers. This is a simple example with the transform in the middle. We've got, let's see, what, 60 hertz, and I guess it's just doing 10 volts there. I don't know, let's step it up, 120. Set that. We've got roughly 120 on the other side too, so this is a 1 here. We can just enter a ratio, primary inductance, coupling coefficient. Also enter saturation current. Got 1000K resistor on the other end. That's So I didn't mean to remove some plots here. New scope. Let's turn off the current. The moment. Add an existing. Whoops. Gap. What I want over there. Scope. Here we go. All right, you'll show that the current here is 180 degrees out of polarity on both sides. So basically what we're expecting to see. Now let's look at some other stuff. All right, let's see what happens with DC and where this becomes problematic. Now you'll notice the milliamps is going steadily up here on the left, steadily down on the right. So the current is building up back through the battery. It's just going to keep building up, generating more heat. Eventually, in real life, the battery would probably explode or at least otherwise fail. So this is why you don't use transformer with DC. Well, at least without an interrupter. And then if you want to do step up, is going from 10 volts to nearly 100 volts. You'll notice the current is actually, well, it's alternating here, but it's like the current's actually going down even though the voltage is going up. Then with the step down, we're basically doing the opposite. About 100 and okay, we're doing by RMS here. 120 RMS to 12 RMS over here. So, stepping down. And of course, we'll actually notice a smaller current on the left and a bigger current on the right in this case. I think any of the other examples are necessarily useful. Oh yeah, long distance power transmissions, satchel for nothing I'm really going to get into right now. What about transformers for hobby usage? Well, many of the transformers obviously are completely unsuited for hobby electronics. They're large, expensive, made for extremely high voltages. Even a connection to AC can be extremely dangerous. But there's plenty of small transformers for signal logical audio usage that you can get out there. The most common ones I find are usually audio transformers. And they're used for audio isolation to reduce ground loop feedback. Since again, using a transformer isolates circuit because electrical energy is transformed. Same thing with signal transformers. I've generally seen them used to isolate and clean up rectangular waveform signals because, again, it isolates the circuit. There's pulse transformers. They usually provide a wide pulse width, short rise time for converting voltage, isolating circuits, and so on. All right, let's go to QSpice and take a look at a very basic transformer setup here. On the right, we've got a sine wave. Let's just say that represents an audio signal. It's running through a resistor here, and it's running to something that represents a primary coil. And then the stuff on the right represents the secondary coil, so our input or output. And it also has a resistor and a final resistor to ground. So what we're going to first look at, we're doing a transient plot here of over 10 milliseconds, um, with a step of very 10 microseconds, I believe. So we're plotting the voltage of the input, then plotting the voltage of the output. Let's take a look at what that looks like. All right, so on the bottom, we've got our primary coil, what's going in, and then we've got on the top our secondary coil, what's coming out. And it's not exactly one to one, obviously. Um, Both the phase is different and our the output that we're getting is different. All right, we're going to take a look at current now, and it's very small. It's only in the microwatts here, but we've got our primary current, and this is showing how it's being transformed to the secondary as well, how the energy is being transformed. Very similar idea to how it worked with voltage. All right, let's wrap things up. A transformer is a passive component. It's meant to convert AC voltages through induction, which isolates the input, and the output circuits can be used for DC voltages, but that's a whole other bag of worms. Law of induction, Faraday's law of induction explains magnetic flux generating electrical energy. Inductors and transformers do both use induction, but they are different components. Conversions determined by a ratio between the primary and secondary coil windings. There's a volt amp rating for each transformer indicating the maximum power capacity, and usage generally shouldn't exceed about 80% of that. Most transformers are completely unsuited and maybe even really dangerous for hobby electronics, but you can use circuit simulators to kind of simulate ideal versions. There are smaller transformers, audio, pulse, signal, that can be useful for a lot of hobby electronics, and they are much safer. Well, until next time, have a good one.